In this video, we are going to continue looking at electrophilic aromatic substitution. And in particular, we'll be looking at the effect of deactivating groups on electrophilic aromatic substitution. So remember, EAS, or electrophilic aromatic substitution, looks like this, where we are replacing one of these hydrogens for some kind of electrophile here. And this is happening on an aromatic ring. And aromatic rings have these different resonances, and this is what gives rise to the electron donating group, electron withdrawing group, and as we'll see in the next video, the halogens have their own special effect on these types of reactions. So the resonance for the electron donating and electron withdrawing groups look like this, where we see with the electron donating group, we end up with lone pairs and negative charges being spread throughout our ring, whereas with an electron withdrawing group, we end up having these positive charges and a loss of electrons throughout the ring. And so that looks like this if we look at the electron density, where we have for an electron withdrawing group, such as this benzaldehyde, that the electron density within the ring goes down relative to the benzene. Where we saw in the previous video, when we have an electron donating group, such as with phenol, that the electron density within the ring actually increases. And the types of groups we have look like this. So as I said in the previous video, we looked at these ortho-para-directing activating groups. In this video, we'll be looking at the meta-directing deactivating groups. Then in the next video, we'll look at the halogens, which are going to be ortho-para-directing but deactivating. And so, like I said, we're looking at deactivators. So they're called deactivators because they decrease the rate at which the electrophilic aromatic substitution occurs. And so we are going to be slowing the reaction down, but we're also going to be directing it towards the meta position. So remember, meta looks like this, where they are on these carbons here relative to our group right here. So we saw in the previous video that the electron donating groups are ortho and para directors. This one is going to be a meta-director. So some of the electron withdrawing groups, the one that gets used quite often is nitro groups, but we can also have sulfonate, cyano, and carbonyl. We'll be looking at mostly the nitro group. We'll take a small look at carbonyls, but all of these kind of work in the same way. And so if we look at the nitro group here, nitrobenzene is about 100,000 times less reactive than benzene. So remember, we are slowing things down, and we're slowing it down at all positions. It'll just be slowing it down less at the meta position. So nitration proceeds slowly, and this gives the meta isomer as the major product. So we see here we have our nitrobenzene. We run this EAS reaction, and we get 93% meta. We get very little bit of ortho and even a smaller amount of para substitution in this case. So an electron donating substituent activates primarily the ortho and para positions, but an electron withdrawing substituent, such as our nitro group, actually deactivates primarily the ortho and para positions. So like I said, this is deactivating all of them, but it's mostly deactivating at the ortho and para positions. And because of this selectional deactivation, instead of meta-directors, these are sometimes called meta-allowing. So remember, we're not activating it at the meta, we're just deactivating it less at the meta. And so meta allowing is maybe a little bit more accurate about what's actually going on here. And so the reason this is happening is because we have these positively charged atoms right here bound to the ring, and so these can actually have an inductive effect. So that inductive effect will actually pull electron density away from the ring, and so that will cause it to be electron depleted, and therefore it will react slower. And so what we see is if we have an ortho attack here, then what we end up having are these two cations right adjacent to each other. And so that's going to be very unstable, and so very unlikely to occur. Similarly, when we do the para attack, we end up with these cations right next to each other. And so that's going to be unstable, that's going to be less likely to happen. Whereas if we have the meta attack, we don't end up having that as one of our resonance structures, and so that's why the meta attack is less deactivated than the para and ortho attacks. And so again, what we see here relative to the benzene right here, the meta is deactivated. It does become higher in energy for the transition state, but the ortho and para are even higher. And so that's why it's going to end up being a meta director, because the meta is less deactivated than the ortho and para. Then if we look at this for carbonyl groups, it's roughly the same type of thing going on, where if we try an ortho or para attack, we end up with a positive charge next to the partial positive on carbon, and so that's going to be less likely, it's going to be less favorable, but we do not end up with that when we do the meta attack. So then the positive charges will either be on this carbon, or this carbon, so they are not adjacent to that partial positive on the carbonyl carbon there, and so that's going to make it meta directing or meta allowing, because it's going to make the ortho and para attack less likely than even the meta attack. And these are some of our deactivating meta directors. We saw the nitro already, but we can also do this with the sulfonic acid, with the cyano group, and we can do it with our carbonyls here, but we can also do it with a quaternary ammonium, where we can see that if we have this bound there, that's also a positive charge that will then be adjacent to a positive charge in our sigma complex. And so that is why these are deactivating and also meta directing. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.